Today, we'll be looking at the Langchain autocoder, which builds entire LLM chains and agents just from simple descriptions. This is possible because I have downloaded the entire Langchain documentation, all 1033 URLs, plus I have extracted each and every meaningful atomic code block with explanations using GPT-4. This process cost me almost $80 in API. And I have embedded it in code embeddings.csv, so we can actually do similarity search over and let GPT-4 write the Langchain code that we're looking for. Let's take a look at how it works. All we have to say is just ask it an agent with memory and SERP API search tool, and it will retrieve all the necessary blocks of code, and then it will write our code for us. Once the code is complete, it is written into response.py file. You can examine it, and if there's any issues, you can quickly fix it and just run it. And we have our SERP API search with conversation buffer memory. We can ask it to write 3 LLM chains which work together to write a story. Again, we retrieve our chunks, and our autocoder is writing our Langchain code. It's setting the template, character template, plot template. It's setting the chains, setting chain, characters chain, and plot chain, giving it a title, and it writes it to the file, response.py file. We can ask for 5 sample document loaders, and it's doing the unstructured file loader, text loader, API file loader, and TensorFlow dataset loader. We could have also specified exactly what we needed. And here we have all our loaders. We get some warning because we haven't imported all of them. Sorry, actually there was some text included in between the codes, but here we go. We have 5 different loaders explained, including S3 file loader. So you can use this system to build any kind of Langchain code that you're looking for. The process to build this is quite complicated and costly to extract the code atomic blocks. I will have both the datasets and the code available at Patreon. Link will be in the description. We first have a docs crawler file, which crawls given a certain domain. This can also be applied to any other documentation domain. Finds out all the hyperlinks and scrapes over them and downloads them and saves them to file. This is how we have attained all the URLs as files as such. And we have our extract code in parallel file, which uses 2 GPT calls, one with GPT 3.5 16K and one with GPT-4. The first one checks if a documentation contains any code or not. And the second one uses function calling to extract an explanation plus the code pieces, which are self-sufficient and atomic in nature, and returns them. And then we parse them out of the response and actually save them into files of their own under extracted code folder. After that time, we can actually initiate our search embeddings. After we have used our embed.py file, which actually embeds the code files and their embeddings after creating them into code embeddings.csv. We are using threadpool executor so that we are also performing the embeddings in parallel using concurrency. And we are using tenacity for all GPT calls, including the embeddings, to make sure that even if there's any errors that we can retry and continue the operation. The extract code in parallel is what cost me the most, which is almost about $80. But I was surprised that this code actually ran without a single error. It took about 30 minutes with 8 workers working concurrently. After we have crawled the documentation, and after we have extracted the code, and we have embedded them, then we can actually use the search embeddings py to find the similar documents from our embeddings vector space, and then actually make a call to ChatGPT to return the proper code that we are looking for in Langchain. As I said, this was a very costly project for me. I will be making all the code plus the dataset along with embeddings available for Patreon supporters, and at a lower tier, I will be making the code available along with the original crawled documentation if you wanted to embed it yourself and extract the atomic code blocks. So 2 different pieces of code will be available at Patreon. All of the code will be available at AI Architect tier, and all the code without the data set will be available at connoisseur level. If you do become an AI Architect patron, then you will be able to download advanced projects such as AutoAGI, which is an agent that actually works and writes its own tools, along with exclusive code review content. Let's go over the code files one by one. We will start with the crawler. We are at first doing all our imports. We are defining an HTTP URL pattern, and we are giving it a main domain name and a full URL, which is going to be our starting domain. So we will start crawling in this domain, and we will look for every hyperlink, but we will make sure that we never get out of this main home domain, because we don't want to look into the URLs which are outside of the documentation. When you're doing crawling or scraping, always make sure that you are allowed to do so with the website's terms and conditions. First class is the hyperlink parser. This one is a custom HTML parser to extract hyperlinks from HTML content. This class extends the inbuilt Python HTML parser to specifically find and install all the hyperlinks present in the given HTML content. This handles each starting tag in the HTML content. For each anchor tag, this method extracts the href attribute, if present, which is the hyperlink, and adds it to our list of hyperlinks. GetHyperlink method for the hyperlink parser class retrieves all hyperlinks present in the HTML content of the given URL, and then the URL whose content we want to parse for hyperlinks, and returns a list of hyperlinks found in the URL's content. Other method, getDomainHyperlinks, filters and processes the hyperlinks to ensure they are within the given domain. This function first retrieves all hyperlinks from the provided URL's content. It then processes each link to ensure it's a valid URL within our domain of interest. This main function, which is a function that is outside of the class, is the one that drives the crawling process. This function sets off the crawling process from a given starting URL. It ensures that only links within our domain of interest are crawled, and it saves the textual content of each URL to a file for future processing. As we can see, this is the process, and then we just run that main function. Once we are done with the crawler, then we will have downloaded all Langchain documentation into this folder. As you can see, there's 133 URLs and 1.5 million tokens in total. After that, it is time to extract the code from this documentation. We will need OpenAI and TikToken and Tenacity. We are importing logging and setting up logging for Tenacity. We have this function, count tokens, which just counts the tokens that they're using GPT 3.5 turbo encoding. And this is how we can do that. We just return the length of the encoded string. Because we will be checking the length of the documentation in tokens, and we'll be doing some model management based on how many tokens we're dealing with, since GPT-4 can only handle up to 8,000 tokens. And we want to skip any documentation if it contains more than 16,000 tokens, because GPT 3.5 Turbo 16K can only handle up to 16,000. And we are setting our tenacity to retry in an exponential fashion with a multiplier 2. This allows us to start from 1 second if this API call fails, and double it with each failure. For example, we will try 10 times. We will start with 1 second of wait in the first failure, then 2 seconds, then 4 seconds, 8 and 16, up to 60 seconds, because our multiplier is 2. And we are attempting it a total of 10 times. So we are defining check if code present function, which we are going to use GPT 3.5 Turbo for, which takes in a doc, a model, and currently max tokens, which we are not using. So we are actually giving it the text, right? We are going to give it a piece of documentation, and we're going to ask, is there multiple lines of Python code present in the provided text? We're setting the temperature to 0, max token to 1. We're giving it 2 tokens, one for yes, one for no, and we're setting its logic bias to 100, so that we're forcing the model to return either yes or no based on this question. So this was actually really difficult to achieve. If you try it yourself, you'll see. Then we just return the response is yes or no. Then we have our other call to GPT, the extract code, which is a hefty system message, but essentially it just asks it to extract essential code pieces, self-sufficient code pieces, and to explain them, and then to return them. and we give it the documentation, and we have a function call with streaming through. We just essentially are trying to get the explanation and the code, okay? And then this is what we will return. A trick that I've learned actually is if you want to avoid JSON loads encoding errors, decoding errors, then you can actually enter a little prompt like this in the function call, and it reduces the misformatted JSON errors. As you see, we are specifying double quotes within strings must be escaped with /. Single quotes within strings will not be escaped, such and so. And this is to get the streaming response. Then we return the process text. Then we have a write code function, which takes in a file name and extracted code with explanation. We get the explanation out of the GPT and actually we comment it. And then we add the code block right after that. And then we write it to a file. We are setting a function to process a single file right here, which essentially opens our first crawled files, right, from this folder, and then assigns it to a doc. We are setting this, we are encoding and decoding from ASCII to not have any issues with non-UTF-8 characters. We are defining a process single file because down the line, we're going to be using thread pool executor in parallel by calling this to process multiple files at once. Then within the process single file function, we actually start counting the tokens for that documentation. If the token count is over 15,500, we are skipping because it's greater than almost close to our limit. If it is less than that, I still would like to get at least 600-700 worth of tokens of documentation. That's why I'm setting the limit like that. If we hit this condition, then we just return simply. And then we check if the code is present with GPT 3.5 Turbo 16K. We want to do this because we don't want to send the documentation pieces which don't contain any code, which are quite a lot, to GPT-4 to save on tokens, right? So we check if code is present in the documentation when we receive true or false. Yes or no. Then we open the process files just to keep track of which files we have processed. As you see, it'll create a text file like this at the end. And we write the file name because we've now processed it. And then we check if the code is present. Then we check if the token count is over 5,000. I just not arbitrarily selected 5,000 because I thought I'll give about 3,000 tokens just in case for the extracted code pieces. If it is more than 5,000, then I send it to GPT 3.5 Turbo. If the documentation piece that we're dealing with is less than 5,000, then I send it to GPT-4 to make sure that nothing gets cut out. And then in both cases, we run the extract code function and call the appropriate models with the documentation we're dealing with. We check and make sure that process text return from the GPT API call includes extracted code with explanation. And in that case, we remove the last 4 characters of the file name, as you see, because it ends in .txt. And because we want to enumerate it, each one of these URLs, actually, which are saved in text files, will be divided into multiple chunks because we did ask to extract code pieces which are self-sufficient. We didn't want to embed a single entire URL into a single row. We wanted to split it up. That's why we enumerate over the process text, extract code with explanation. Okay, and we get, while we're enumerating, we name the file name with the enumerated numbers. And then we simply write that to file. Otherwise, if that file exists, if for any reason we had to restart this process, then we skip the files that we have already written. And then we have our main function, process docs, which just gives the directory which we're going to be dealing with. We set the mix workers to 8 for thread pool executor. We get the text files list from that directory, which are all the files that we have crawled from the URLs, from the documentation. Then with thread pool executor, we set the futures, submitting each one to the process single file function. And as they become completed, then we actually return the result, meaning we run and complete the process single file function. And that's it. And then we run process docs. When we run this, then we get this folder, extracted code, which includes every URLs, atomic and self-sufficient code blocks, along with explanations for better similarity search. And there's 2,641 of them, which are generated from 1,033 Langchain URLs. I have a sequential extract code file as well, but if you set max workers to 1, then you will achieve the same effect, but I will include the sequential.py as well, just if you want to take a look at it. Now that we have extracted all of our code and saved it into extracted code folder, we can take a look at the embed.py file, which is going to create the embeddings and save it to a CSV file or a JSON, and we'll talk about the difference. Whenever you're using OpenAI, right, make sure to set your key. Here's an example of doing that. We will be using Langchain's OpenAI embeddings just for simplicity purposes. We will again be using thread pool executor. We'll be using pandas to get our vector DB set up, tenacity again, and we have set up logging. So here we have embed item, which we are using the embeddings model, embed documents. And our embeddings model is OpenAI embeddings from Langchain. And we just simply return the file name and the embeddings, because this function takes a file name, a file content, and embeddings model. Next function is create empty embeddings df. This just creates a pandas data frame with columns, code, and embeddings, and this is an empty data frame, just returns it. And then we have a function to add the code to our data frame. We give it the folder path, which is our extracted code folder, and then embeddings df. Our embeddings df, right, was the empty embeddings df, which we have created right here. Df stands for data frame. We get a list of all files in the folder path, which is going to be our extracted code folder. Then we loop over all the files, read them, make sure they're all UTF-8, and we ignore any errors. And then we add to as index of the file name. We add to our embeddings data frame as the file name as the index, and we add it and we return that embeddings data frame. And now here we are at the main function, embed concurrent, which takes in a folder path, embeddings data frame, which we have created, embeddings model, and we just set the max workers to 10. You can increase this if you like. And then with thread pool executor, we are going to run the embed item on each one of the code files. And then when we return it, we actually put it under embeddings data frame under embeddings column. So now, once we are done with that, our embeddings is going to have a code column and an embeddings column. So now we can run all these functions. We first create our empty embeddings, and then we add our code to that embeddings. We're just printing some stuff for information purposes. We define our embeddings model, and then we embed concurrently all the extracted code. And then after our embeddings are retrieved from OpenAI, then we can actually, we have our data frame created. We can save it to a CSV file, that's code embeddings.csv, or we can save it to a JSON file. Now the difference is when you're saving embeddings to a CSV file, then the list of the float numbers, which are the embeddings, gets converted into a string. And when you're loading them, you then have to reconvert it back to a list. And this CSV file ends up being almost 400,000 tokens worth of embeddings. So it can take 30, 40 seconds. But I believe if you were to save your embeddings to a JSON file, you won't have to do that step, although I'm not 100% sure. Next, we can look at how we are doing the search and the GPT call. So now we are looking at the search embeddings.py file. We are again using OpenAI embeddings from Langchain, and we are importing cosine similarity from OpenAI. We are again going to use embeddings because we're going to have to embed the user query, right? I will be making a live stream on this and maybe a few other videos to explain all this. Maybe run it in debug mode. I just don't want to make this video too long. But we do need to embed the questions. We have already embedded all our data sets, right? All the code into code embeddings.csv. But we're going to have to embed the user question and perform cosine similarity with that vector that is the question over all the entire database of vector embedding, so we can find out which ones are similar. We are importing tick token. By the way, the requirements are listed here, will be available at Patreon. Before I continue, I just want to mention my website where you can search all my videos. It's echohive.live. You can find all my videos here. You can find all the videos that you're looking for example, on Langchain. It's an instant search. You can also click on the code download links and it'll take you to Patreon so you can download it directly. Okay. So it's pretty cool. This just is to simplify. You can read the descriptions as well. Link will be in the description. It's echohive.live. Okay, back to the code. We are going to use pandas, of course, and some other libraries. We are using term color to be able to print colorfully on the terminal. So we first will load embeddings.df function, which loads our embeddings from the CSV file as a data frame. And this is the part I was talking about. Because the embeddings column is converted into a string when saving as a CSV, then we need to reconvert it back to a list using this expression right here. So we are saying apply to this column of this data frame some NumPy array eval operation, which then converts it to a list. And we just return that. Again, we have the same embed item function, which is going to embed our query. We have the same count tokens. And then we have our search embeddings function, which takes in the data frame, takes in the question. Here we set a default of 3 return values. Pprint set to true. Actually prints a preview of all the retrieved chunks. N lines is how many lines of the retrieved chunks we will be printing. You can set this to false and you won't print any of the retrieved chunks. If you set it to true, you can increase this N line so that more lines of the retrieved chunks will be printed. So at first we embed, of course, the user query, which is going to go into this function using our embeddings model, and we get that embeddings. Now here is the interesting part. We are going to actually create a new column in our data frame, which had the code and embeddings column already. We're going to name this column similarities, and then we're going to apply, to the entire embeddings column, which includes all the rows, 2,641 of them, and we are going to apply cosine similarity over each one of the rows using the embedding, which is our embedded query. And then this is going to result in a number up to 1, right? And that's going to be our similarity score, for example, 0.95, 0.8. The higher the number, the more accurate the similarity is. And we are going to write each row similarity score in the column similarities. And then we are going to sort it in a descending order. So our new data frame, which is res, is in results, is actually sorted by similarities in a descending fashion so that we can now take the top n many, whatever we have set when we are calling this function, for example, 3, 10, or 20, whatever, many most related chunks, code files in this case, related to the Langchain, and assign it to this data frame. Here we are setting some colors because we just want to print each retrieved chunk in with a random colors just to separate it. This entire pprint is just to actually print the retrieved chunks on the terminal. It has nothing to do with our operation. This is for information purposes only. When you set the pprint to false, then you won't even have to worry about that. Then we just simply return that sorted data frame. Then we set our embeddings model to be OpenAI embeddings. You can set your key right here as well. Then we load our embeddings.df. Remember, this is where we were loading our vector database from the CSV. And now we're defining a ChatGPT class, which just has a system message, right? This is its init method where make sure you include all the imports in the code, define everything in the code. So this is just to direct it, okay? And we have a method to take in user input. We have a method to add messages to the messages we have defined right here. This is right. It's just going to take in content. Role is going to be whatever role and content we give it. So this add message method is pretty general. I have a clear message method just to clear all the messages except the first one because it's our system message. Feel free to add different methods here or use them as you please, however you see fit. Then we have a get GPT response method, which essentially adds in the user input, which is going to be the question. We are using GPT-4. We have streaming true, and essentially we just get a response, and we add that response back to the messages, and we return the response. Since this is a class, we are instantiating it as LC bot, that is Langchain bot, right? We are starting a loop because we want to continue querying it. And we take in a user input, which will be a Langchain related questions, such as the ones we have looked at, such as an agent with tools or agent with memory, some kind of chain-like structure, which you want to maybe create stories with, whatever you like. And then we are going to perform search embeddings with the embeddings DF with the query. Here I am returning 20 retrieved chunks because our chunks are very small. In this case, the 20 chunks ends up being anywhere from 2,500 to 4,000 tokens. Feel free to experiment with it. We are setting pprint to true and then lines to 1. Like I said, this is for informational purposes. And then we are just printing and then we get the related code. Because our related code is going to be a data frame, we want to get the code columns values, and then we want to convert it into a string like this, and then we just print the token count of that, and then we add that message saying that return only the code which answers the user's question based on the context. So what we've done here is that in the class, when we instantiate the class, we already start with a system message, and then we are using the add LC bots, which is the GPT chat class's add message method to add this user instruction, return only the code which answers the user question based on the context provided. Then we add another message saying this is our context, and we add our context, which we have created right here from searching over embeddings. And then we just get a response by calling Langchain bots get GPT response with the query. Okay. And then we just print the total number of the count of all messages. We just want to take a look at the token count for information purposes. And then here I am clearing all the messages. If you want a more chat-like experience, you can actually comment this out and have a more fluent conversation with the bot. Here I am actually having one-shot, outputs. This works well about 7 out of 10 times. If you have a problem, you can just debug it. Obviously, you get this whole code, which you didn't have to write yourself. But like I said, if you do comment this out, the messages will remain in the history. And simply, I'm wanting to write all this to a response.py file. I'm extracting the code from the triple backtick Python, the usually how GPT returns Python code. I'm just simply writing it, and then I end up with something like this. Then I can run it or modify it and use it however I like. As I said, the code files for this will be available at Patreon. Now, the crawled dataset, right? The unprocessed crawled dataset, along with all the code files that we talked about, will be available at the $30 connoisseur level patron tier. And the extracted code, okay, which costs quite a lot of money to create. As far as API costs, it cost me $75, I believe, or $80. And the code embeddings doesn't really cost that much, maybe $1, will be available at the AI architect level. The AI architect level has access to all the advanced projects, plus more times with the office hours, which I have started. Also, I wanted to mention that I've started office hours and I'm posting schedules here. If you're a patron, please make sure to take a look at it. When I'm online, I post the Google Meet link here. Next one is on tomorrow, my time, but anyway, Sunday. Yeah, so the higher tier you are, the more time you get to spend talking with me. Also, you get access to some exclusive videos, the higher that you are. One other advanced project that is currently available for AI architects is the Auto AGI, which is an agent that actually works and writes its own tools. I'm really proud of this project. I think it works great. Take a look at it if you get a chance. Also, don't forget, you can search all my videos and find code download links at EchoHive AI Academy. It's echohive.live. Link will be in the description. Thank you for watching. I hope you found this video useful. I'll see you in the next one.